session. My name is Damian Grzechca. I'm going to be the chair of this session. Every speaker will have 15 minutes slot for the presentation and questions, some remarks from the audience. I have some indicator here. If you will go to the end of this time, I will show you 3 minutes, that left 3 minutes that you should go to the conclusion, and 1 minute is the mandatory part that you have to finish your presentation. So today the first presenter is Mehmet Bozuyla. He will present a novel safe merging algorithm for connected vehicles using NetLog. Okay.
Dear Chair, ladies and gentlemen, you are welcome to my presentation. Title of my work is A Novel Safe Merging Algorithm for Connected Vehicles Using NetLogo. My name is Mehmet Bozuyla. I have prepared this speech with Professor Tola and Professor Murat, and I come from Pamukkale University in Turkey. What will be talked today? Firstly, I will consider a new intelligent transportation system, which name is Metro Car Transportation System. We will shorten it MCS. After that, I will explain tracking and merging algorithm for that system. In the end, I give you some simulation results for that system. Firstly, I want to ask you a question. Is there any major city in the world in which traffic congestion is not a problem? I think all of you say no. Yes, traffic congestion is mainly a problem for us, especially crowded cities. Stress, tiredness, and other psychological problems for the driver, and pollution and noisy. Many researchers work on traffic problem, same as. We propose a solution for traffic congestion with this work. Before our solution, we can remember some vehicles to use in the big city. Personal car, taxi, bus, tram, metro, and driverless car. That's new solution. Let's compare these vehicles by cost, time using, traffic, must use other vehicles or walking. The public transportation systems, bus, tram, and metro cheaper than others, but we can't use. We must use other vehicles or walking to go station. Maybe we buy to moving time. We can use our time to taxi, bus, tram, and metro, but we can't do this with personal car. Driverless car is best solution for time using and must to use other vehicles or walking. We mustn't to use other vehicles because driverless car is special for us. We want a solution to merge the positive features of that systems. Name of this system is Metro Car Transportation System. You are seeing a photo. In this figure, you see Metro car vehicles on grey-separated road. MCS driver can use their time. Maybe she is reading or eating, and he is texting. And driver of MCS is little than normal cars. and roads of MCS is great separated roads. That means there aren't any pedestrian or animals, just for MCS cars. MCS, the vehicles of MCS is little than other cars, so we can effectively use roads. We use roads effectively. You are see a metro car city imaginary. In this colored one, roads are metro car roads. The others one are normal roads. Maybe firstly a driver controls his car to bring MCS station. After this station, MCS controlled controlled vehicles and take away the target station. After this point, the driver take control of his car and where he wants to go, it can go. Yes. That's metro car features. Metro cars system suitability, low cost, comfort, hygiene, security, no traffic jam, effective time using, no traffic lights. We want merged driverless car and metro system with metro car system. Let's compare metro car, driverless car, metro and personal car features. The green ones are positive, red ones are negative features. You are seeing other the infrastructure cost, all of features of metro car positive. Infrastructure cost of metro car, it need a new infrastructure, but we think it's not sorry. With metro car, we propose to combine positive features of driverless car and metro car. We must build new roads for MCS, but it will not be as expensive as metro. After the MCS general information, we could talk about some algorithms of that system. First one is tracking algorithm. You are seeing pseudocode and equation of this algorithm, and this photo shows by the time how the real cars moving with tracking algorithm. With tracking algorithm, we control speed of rear car, use speed and position of rear and front car. We want a suitable gap between two cars to prevent crash. We use that's pseudocode and that's equation. That's merging algorithm. With merging algorithm, we want to control cars on two lane. That's secondary road and that's main road. We separate three parts to our main road: self zone, control zone, and critical zone. On self zone, a car speed up and he want to go the suitable speed for communication, and in the control zone the communication is start and main car and secondary car communicate each other. In the critical zone, we are seeing that the red car, we assume that it's front of that car, that's blue car, and the tracking algorithm working run in this station. We use speed and position of the position of that cars, and compare them to provide the lineup that's position. Before simulation results, I want to talk about NITLogo. NITLogo is a multi-agent programmable modeling environment. It's operated by Yuri Walensky and developed at CCL. It's a free software, a simulation modeling environment. Yes, now I want to give you a simulation result. That's a video. There are 3 cars on this way, blue one, black and red ones. The red car is stopped and the others speed up by the time. Yes. The speed of blue and black car speed up. The destination between 2 cars. When they come to near yes. Sorry. Yes. That's merging algorithm. There are 3 cars again, but the black one on second row. Let's watch it. By the time the gap between that car is opened and the black car merging the main road safely. We are seeing they are lined up. Next one. The secondary and main road organization. All of second road car implement main roads safely. For example, that's point the main road and secondary road on same position, but by the time main road speed up and secondary road speed down, and they are lined up over the merging zone. Yes. I tried to give you a lot of information in a time. Thank you very much for your attention.
Thank you. Okay, so let me open the discussion. Do you have any questions, comments, remarks to the presenter? If not, I have a question.
Yes.
Because the distance between cars also depends on how often you obtain the position. What is your assumption for obtaining the position for a particular car? Do you use something like a GPS in a particular manner? You know, I'm not talking about the simulation, because in the simulation you just take into account that you have the position all the time.
Okay.
But in general, real environment, you have to take into account the acquiring position, and it takes some time.
Yes.
So what is your solution? Because according to the GPS, you have usual time between the position is something like 1 second. So it reflects to the speed and the distance that you can have between the following cars.
We will to use DCRC communication. and maybe with cable communication. But every tow time we take the tow 10 milliseconds. Every tow time or algorithm working. Maybe the next works we will change that.
So right now you just
Isolate.
okay.
Yeah, thanks.
Something like that. We haven't get the account right now.
Okay, but you have to take it if you want
Yes,
to apply it in the
yes.
real environment.
Yes, on next.
So either GPS or something else that will fulfill your requirements. Okay. Questions? If not, thank you again.
Thanks.
And next presenter is Christian Kanchev, and he is going to present modeling and control by neural network of electric vehicle traction system. So he is from Bulgaria. Yeah, so take your time.
Mr. Chairman, ladies and gentlemen, my name is Christian Kanchev. I'm an assistant professor at the Technical University of Sofia, Bulgaria. And today I'll present you our work entitled Modeling and Control by Neural Network of Electric Vehicle Traction System. My presentation is composed of the following major parts: a brief introduction, presentation of the model system, then I'll talk about the implementation of the neural network control of the BLDC, brushless DC machine. After that, I'll present you the simulation results and conclusions. So, as an introduction, one has to say that the main advantage of electric vehicles is actually the lack of local pollution. Pollution is produced at the point of generation of electricity or where the vehicles are manufactured, but local pollution in the cities by using electric vehicles isn't produced. Therefore, they are interesting for research, and this paper is focused on the modeling and control of an electric vehicle. It is a hybrid system composed by a battery and a supercapacitor. And in this study, we have implemented a normal neural network for control of the BLDC machine. The mechanical model comprises a gearbox, a single mass mechanical model, and a model of the road wheel grip force. All the masses and inertia, as it is a single mass mechanical model, they are expressed relative to the rotor of the electric machine. And the vehicle is modeled and studied with two driving cycles, an urban cycle and a suburban highway cycle, and an assessment of the recycled energy due to regenerative braking is performed. So the structure of our vehicle, on a common DC bus through DC-DC converters, we have a battery and an ultracapacitor, and the BLDC drive, which is composed of a three-phase inverter and a brushless DC motor. So they are connected to bidirectional DC-DC converters that I'll present in the next slide, and the BLDC motor is controlled by a normal neural network. So the control of the electric vehicle is composed in two parts. First, with different timescales, of course. The first one, level 1, is the energy management, identification of the mode and distribution of the references among the sources, with a time scale of about 1/10 of a second. And the second one is control of the power converter switching and setting of the duty ratio and closed loop control with a time scale of 1/10 of a millisecond. So in this work we have implemented the neural network here, but our ultimate objective for future researches is to implement the neural network here for identification of the mode. So identification of the mode in this work is done by a determinist algorithm, and the power references sharing is done by this schematic. The battery reference is performed with a low-pass filter, and as the ultracapacitor is able to sink or supply large amounts of power, of instantaneous power, so when we pass it through the low-pass, we have the battery reference, and the ultracapacitor is the rest, actually, reference. So the power converters are bidirectional synchronous buck converters. They are able to operate with proper control. They are able to operate in buck mode when transferring power in one direction, and in boost mode when regenerative braking is performed. By proper sizing of the circuit, we have proven that we can use an average model. So the average model, the in-buck mode, it is modeled like this, with the duty ratio D. This is the output input current and the output and input voltage. And by regenerative braking, it is modeled also by an average model with these equations. Now next one, the brushless DC motor. Actually, it is the rotor position is encoded and decoded by a Hall sensor, encoder and decoder, which ensures adequate switching of the inverter. So the voltage is fed to the stator windings are the average values of the DC voltage applied in function of the rotor position. The BODC machine is modeled in a rotating reference frame, in a DQ reference frame. Actually, this is the Park transformation matrix which is applied, and theta is the rotor position angle, which is actually proportional to the field angle and the number of poles, which in our case is one pair of poles. Then the machine torque is expressed by this equation, which includes the rotor flux, the synchronous inductances on the D and Q axis, and the currents on both axes. As the DQ axes are an abstraction, actually for measurement purposes we have to apply also the inverse Park transformation in order to know the currents flowing through the three faces of the stator winding. Then the mechanical model, it is modeled by a single mass mechanical model. This is the equation where this is the total inertia relative to the rotor, the mechanical torque of the machine. No, actually this is the mechanical torque applied to the machine rotor, and this is the electromagnetic torque of the machine, the force applied to the rotor, and the angular velocity. The mechanical model comprises also a reductor, wheel, and a model of the road wheel friction force. Here is the reductor, the gearbox, modeled with these equations, the wheel modeled with these equations, and the contact road wheel, which is modeled by this function. Here is the dry contact. If we have a wet contact, it will be proportionally lower. By applying this type of disturbance, we were able to test the motor control. Actually, we have even applied an extreme disturbance at a magnitude of 0.55 from the total force in order to test the control of the neural network. So the whole model in Simulink with the closed-loop normal control is this. Here is the implemented neural network. It has two layers, a nonlinear and a linear layer. Training is performed by batch data, and plant identification process is done by a MATLAB tool, NARMA L2 tool in MATLAB. The mathematical function implemented by the NARMA is this, and the equation of the control function is then obtained. And so the model is composed. Here is the theta angle, then the Hall effect encoder, decoder. Here are this is the inverter, which is actually the NARMA neural network controls the average value of the voltage fed to the stator windings. After this, we have the Park transform, ABC to DQ transform. Here we obtain the two currents in both axes. For measurement purposes, we use the inverse Park transform. Here is calculated the electromagnetic torque, and the mechanical single mass model is in this block. And the other blocks of the mechanical model are already mentioned. Then we have tested this model with parameters of three vehicles, each one with its mass, surface area, maximum speed, and average range. Actually, average range depends on the battery and the battery life, but we have admitted that there are new batteries in vehicles. Both driving cycles used for these simulations are the CT driving cycle with very frequent acceleration, decelerations, and stops, and a highway driving cycle with very few decelerations. So the results actually are presented in this graph. This is the results with the city driving cycle for three vehicles and the highway driving cycle. There we could simulate only vehicle 2 and 3 because vehicle 1 doesn't reach the minimum allowed speed at motorway. As some conclusions, I can say that a correlation actually is visible between the mass and the percentage of recycled energy, And simulation results demonstrate that recycled energy percentage is mainly dependent on the driving pattern, on the driver style, and vehicle mass. So as a conclusion, modeling of this electric vehicle is presented in this paper, which is a hybrid electric vehicle with an ultracapacitor and a battery. The system model comprises mechanical, electrical part, and modeling of the power electronic converters and control. The BLDC is closed-loop controlled by an ARMA neural network. This model was tested with the characteristics of 3 vehicles and 2 driving cycles, and simulation results demonstrate that recycled energy percentage is mainly dependent on the driving pattern and less dependent on vehicle parameters. For further developments, we could implement the control of the vehicle modes and power sharing between the ultracapacitor and the battery by a neural network. Thank you for your attention. Do you have any questions?
I open the discussion. Do you have questions to the presenter? Okay.
How many coefficients is there in the ARMA model?
How many coefficients
How many coefficients?
in the ARMA model?
Yes.
Yeah, actually I have prepared a slide with more adequate presentation of the ARMA network. Actually we have 2 hidden layers, 3 delayed plant inputs, 2 delayed plant outputs. And as of the coefficients, they're presented in these equations, actually. So the number of inputs and outputs. So actually, this is the ARMA L2 structure.
Actually, it was also my question, but okay, thank you for the question. I have another one related to neural network, because your disturbance is very simple. You just simulate on the rectangular waveform at the input in order to make some noise. What do you think about applying different disturbance and how it reflects to the behavior of the neural network? Because, you know, in general, the neural network should obtain the generalization ability at the output. So you have only one disturbance and the output.
Yeah, actually, our goal was to model the driving cycles. The disturbance was just for a test in order to compare if the neural network deals with it fine or if the P controller is better. It should be able to handle almost any disturbance because it's trained by itself, actually, by batch data. So I think it should be able to handle more complex disturbance waveforms.
Okay. More questions? If not, thank you again. Okay, our next presenter comes from Slovenia, Grzechca and he is going to present automatic classification of motor impairment neural disorders from EEG signals using deep convolutional neural networks.
Good afternoon, everyone. Thank you for the introduction. My name is Grzechca and I'll present to you our paper titled Automatic Classification of Motor Impairment Neural Disorders from EEG Signals using Deep Convolutional Neural Networks. So my presentation is structured from the following sections. First, we'll go through the introduction and describe the problem which we are addressing. Then I'll present our proposed method. Later on, we'll take a look at the results. And finally, I'll conclude the presentation with some final thoughts. So for quite some time now, the electroencephalogram or EEG is used for diagnosing some kind of neurological disorder in a person. In general, the approach to EEG signal analysis consists of the following steps. So we capture the signal using the electrodes placed on the subject scalp. Then we pre-process and filter the signal, do some analysis and or transformation of signal, and some kind of visual representations, for example, like spectrograms. Well, keeping that in mind, we tackled the problem of classification of EEG signals using the visualization representation instead of raw EEG signals. We take a look at how the neurologists handle and analyzes the EEG spectrograms or visual representations, and try to do something similar with our convolutional neural networks. So while traditional methods of machine learning were not able to match the human performance in image classification tasks, with recent advancements in wide and deep artificial neural networks provided us with near human performance. So based on those presumptions, we set our goals to study whether the method utilizing the deep convolutional neural network can be used to successfully classify a certain neurological disorder. And the second one, how to exactly transform the raw EEG signals into the spectrogram image to feed and learn our convolutional neural network. So the proposed method consists of the following steps. The first step is read and structure the data stored in JSON files for further data manipulation. The second step is pre-processing EEG signals, which consist of the filtering signals, transforming the signals, and finally plotting some spectrograms out of those signals, and finally training and testing the convolutional neural network model. So the dataset we used was made by brain-computer interface research group at Colorado State University in years 2011 to 2012. The dataset consists of 13 EEG recordings, 9 of which are recordings of healthy people, which we labeled as unimpaired, and remaining 4 are the recordings of persons which have some kind of motor brain impairment, neurological disease. Each of the EEG recordings is 3 minutes long, recorded on 8 channels with sampling frequency of 256 Hz and hardware filtering done at 0.5 to 100 Hz. The image below represents the positioning of the electrodes on the human scalps while recording the EEG signal. So steps we conducted in the phase of pre-processing EEG signals. Firstly, we applied butterworth filtering at 0.5 to 7.5 Hz. We use this frequency range based on the previous studies, which has shown that in this frequency range the majority of abnormal brain activity is happening. Later on we performed fast Fourier transformation on those filter signals, and finally we plotted spectrograms of power density for each channel of the EEG signal. Basically, from one EEG recording we get 8 spectrogram images, each image for each channel of EEG recording. Here is presented our architecture of CNN, which is based on the LeCun's 5-layer linear architecture. On the input, we are feeding the CNN with a spectrogram image, colored spectrogram image of size 270 by 202 pixels. Later on, we have 3 convolutional layers and 2 subsampling layers, and at the end we have 1 fully connected layer with output layer which labels the cases as impaired or unimpaired. We created 8 of those models for each of the channel of EEG recording, 1 model. So here is presented, on the left is presented convolutional layer. What it does is basically convolutes through the matrix of the image pixels and creates so-called feature maps. And on the right side is polling or subsampling layer, which takes those feature matrices and subsamples them down, in most cases using the maximization function, which reduces the computational needs. So we trained and validated our method using live-on-out principle. Out of total 13 instances of EEG recording, we used 12 instances for the training and the remaining 1 for the validation. We repeat this process in total 13 times, so each time we leave out a different instance for the validation. Down below is the figure representing the sample of those 8 models. So we have 8 models, each labeling, each training case with impaired or unimpaired label, and joining them together using the majority voting, which gives us the final output of our model. So the results, our proposed method achieved general accuracy of classification, about 69.23%, it correctly classified 1 out of 4 impaired subjects and 8 out of 9 unimpaired subjects. If we compare our performance of our proposed method with state-of-the-art methods, which utilizing medical domain knowledge, feature extraction, and handpick features, is our method lagging behind about less than 5%. But if we look at the comparison of our CNN against the traditional classifiers, we can see that we achieved general accuracy or matched general accuracy of the KNN and SVM classifiers. But looking at the sensitivity of the mentioned classifiers, we can see that none of them were able to properly classify any of the impaired instances. Looking at the F1 score, you can see that our method outperformed all of the compared traditional classifiers. To conclude, what we did, we proposed a method which is in automatic manner for classification of EEG signals using the deep convolutional neural network. The method consists of filtering signals using Butterworth filter and transforming signal on each channel using fast Fourier transformation, then plotting the spectrograms, and finally assembling 8 CNN models utilizing the majority voting principle. While I would like to point out that our method does not require any medical domain knowledge and is without handpicking features and feature extractions, but at the same time achieves high general accuracy as well as F1 score, and it's, like I said, lagging behind the state-of-the-art methods, which do include medical domain knowledge and handpicking features less than 5%. That would be it. Thank you for your attention.
Thank you. I open the discussion. Okay.
How many instances are there in the data set? Input data set?
Total 13 instances, so 13 persons, 13 EEG recordings. 9 of them are normal, healthy people, and remaining 4 are the impaired ones.
I tried shallow classifiers such as artificial neural network.
Yes, we did it. We did compare it, but it performed very poorly.
One more
Okay.
Yeah.
Because when the available training data set is small, for example,
Yes.
in your case,
Yes.
convolutional neural network is not the best.
Yes, that is true, but that was preliminary research. We're planning to use a bigger data set to confirm our results.
Okay, and I have a question related to filtering method.
Yeah.
Because using hardware, you limit the bandwidth up to between 0.5 Hz up to 100 Hz. And after that, you create a Butterworth filter that will narrow the bandwidth up to, I don't remember,
0.5 to 7.5 Hertz.
1.5?
0.5, 0.5
up to 15 Hertz.
7
Hertz.
7.5.
So why you limit the bandwidth of your signal? Maybe you just lose some important data which is outside of the bandwidth.
Yeah, I understand. The problem is it's too many noise in the upper scale of the signal, so the convolutional neural network cannot extract those features correctly. We limited the bandwidth of the acquired signal to 0.5 to 7.5 Hertz because recent studies showed that there is the main brain abnormal activity happening in this range.
Okay.
So 0.5 to 7.5, we just ignored the rest.
But on the other hand, if you take into account EEG, is it possible to acquire the ECG signal from EEG?
That's not
because it
no.
should be the answer.
Yeah.
ECG signal is wider.
Yeah.
It's not limited to 8.5 Hertz. If you want to obtain the pulse, you have to design the filter that is around 20 Hertz, 17-20 Hertz.
Yeah. I'm not so familiar with signal processing. I'm more of a computer science direction. So thank you for.
Okay. Questions? Thank you again.
Thank you.
Okay. Next presenter comes from Turkey, Süleyman Çaben, and he is going to present drive mode estimation for electric vehicles via fuzzy logic.
Dear Mr. Chairman and dear participants, you're welcome my presentation. We work drive mode estimation for electric vehicles via fuzzy logic, and the presentation is occurred 8 headlines, and as abstract introduction and electric vehicle force model, fuzzy logic classifier design and realization, materials and method, experimental study, conclusions and references. Electric vehicles are widely used today. The biggest problem of electric vehicles are limited energy and limited range. Using energy efficiently is an important issue. Using energy efficiently is an electric vehicle systems and power consuming systems in real time. We predicted the optimal driving mode with electronic control unit using fuzzy logic control. We tested system on electric golf car real time. In this picture, is electric golf car is shown. The measurement parameters are transferred to vehicle control unit via control area network. The driver can choose driving mode as economical driving, normal driving, and sporty driving. In this study, a vehicle control system for electric vehicles was designed and realized, and electric golf car is used in the study. The conditions of all subsystems of the vehicle are monitored by the control hardware, and the monitored conditions are transferred to vehicle control unit via the CAN communication line for the vehicle. The current state of the vehicle is monitored in real time on driver's display. The current state of the vehicles is monitored in real time on the driver's display. After the appropriate driving mode prediction is made in the vehicle control unit. The test of the vehicle has been analyzed with the driver in the university campus area, the output performance of the vehicle control unit with the driver and a passenger, and with the driver and 3 passengers. The electric vehicle's drive system must overcome some physical force to perform its motion. These forces are gravity, wind, rolling resistance, inertial force. Figure shows the force acting on the car. Knowing the dynamic and static force that affect the car is very important for the vehicle control unit developed for the vehicle. The driving force required for a vehicle calculated by equations is given, where Ft is a, excuse me, sorry, driving force, and FRR is rolling resistance force, and F wind and the wind is the wind force, and G gravitational force. Three different types of driving modes are recommended for the vehicle driver according to classifier output. There's economical driving, normal driving, and sporty driving. The design fuzzy logic classifier is defined as 6 input variables and 1 output variable. The fuzzy logic classifier input membership functions is shown this picture, and instantaneous power consumption 0 to 10,000 watt, road slope up to 20 degrees, driver gas pedal reference up to 100, battery charge status up to 100%, average temperature up to 80 centigrade, vehicle speed up to 70 km/h, and fuzzy logic classifier output is limited between up to 100. An electric golf car has been modified and prepared so that this exercise can be performed and tested on a suitable platform. The modified electric golf car was produced as 4 people, 1 driver, travel guide and 2 passengers. The vehicle's drive system consists of a mechanically linked electric motor, gearbox, differential system and wheels. A picture of the electric golf car is given in figure. Technical specifications of the electric golf car is given table. The golf cart is length 2,850 millimeters with 1,150 millimeters, height 1,800 millimeters. Motor 48 volts, 100 amps DC current, direct current motor. Figure shows the operation block diagram of the electric golf car. The vehicle consists of a battery, electric motor, charging unit, engine control unit, and motor control unit, motor and motor drive status motor monitoring system, battery condition monitoring system, vehicle height measurement system, gearbox and differential systems. The electric golf car is a model of electric vehicle, the unladen weight of 476 kilograms, reaching a maximum speed of 30 km an hour and carrying capacity of 350 kilograms, which provides power transmission with the single motor differential system. There is figure in this system and A motor control unit, B direct current to direct current convert unit, C in altitude measurement system, D charging system, F motor and motor condition measurement system, G navigation system, and H is a SD card record system. The voltage of the vehicle's batteries is measured with the LAM LV25P voltage sensor, the temperature with the LM25 temperature sensor, and the battery main current with the LAM LA125P sensor. And these used sensor LAM current sensor, RTD resistance temperature detector, and UGN magnetic field sensor, and LM temperature sensor. The communication of the drive panel with the CAN protocol is done via Arduino Uno. After transferring all data measured in the systems to the VCU, it was programmed via MATLAB Simulink, and fuzzy logic classifier was applied to the STM32F4 controller, which is the controller of the system. This picture, the control software is shown, this picture, in MATLAB Simulink toolbox. The MATLAB Simulink blocks for estimating the appropriate driving mode of the vehicle is given in figure, and in input membership functions, power consumption, gas reference, slope, state of the charge, temperature and velocity, and fuzzy logic classifier out. After the vehicle has estimated the appropriate driving mode and estimated range, the data processed in the electronic control unit is sent to the related systems via the CAN line. The transferred CAN line is shown that picture in MATLAB Simulink. Experiments are conducted on Karabük University campus in the real environment of the vehicle. The route map for performing the experiments is extracted from the Google Maps application and is shown in figure. 3 different scenarios were designed with no load, half load, and fully loaded, with the aim of carrying the passenger on the specific route. It is aimed to take the driver's VCU estimations into account when driving as experiments. The average current drawn from the battery during the experiment is calculated as 28.30 and average battery voltage is calculated as 49.31 volts. It is seen that the drops in the battery voltage are caused by the high current values drawn from the batteries. It is seen that the total electrical power consumed is 187 watt-hours. As a result of the experiment, the desired driving mode estimation is done by fuzzy logic classifier. In the 10% of the test period of the vehicle, the driver offers the economic driving mode. The driver recommends the normal driving mode in the 70% time slot, and the driver suggests the sporty driving mode in the 20% time slot. The graph of the battery voltage and the time taken from the batteries during the half-load test are given in figure. The average current drawn from the battery during the experiment is calculated as 46.05 and the average battery voltage is 49.22 volts. The total electrical power consumed is the vehicle is 200 watt-hours. The vehicle's half-load test results show that the most suitable driving mode has been estimated for the vehicle, and the driver's economic driving mode suggested in 12% of the test period. The driver's normal driving mode suggestion in the 86% in the case of the slice. The driver's is offered a sporty driving mode. During the experiment, it's seen is a fully load experiment. During the experiment, it is seen that the total electric power consumed in the vehicle is 280 watt-hour in the time period of 28.8% of the test period. The driver proposed the economic driving mode. The driver suggested the normal driving mode at the time period of 69.7%. The driver is offered a sporty driving mode when the time is short. As a result of the experiment, it is evidenced when the graphs which are made without problem by giving the appropriate driving mode prediction is desired. When the experimental results of the electric golf car are evaluated with 3 different scenarios, it is seen that the increase in the number of passengers in the vehicle causes the instantaneous power consumed in the vehicle to increase. With the VCU developed in the study, the vehicle conditions are taken into the system using CAN communication, and the optimum driving mode is suggested by the driver with the designed fuzzy logic classifier. As a result of this work, a new central control system which can be used in electric vehicle technology has been introduced and implemented. A new method has been developed which suggests a driving mode for the vehicle driving depending on the instantaneous status of the systems in the vehicle. Future work on electric vehicle control can inform the driver of the vehicle and limit the use of the vehicle by directly interfering with vehicle systems. Also, the status of the system can be monitored so that the vehicle can go from the current position to the target position. And it can be predicted whether the vehicle can reach the target according to the existing parameters. You can contact that, write this email address for your questions. Thank you for listening to me.
Thank you. I open the discussion. Questions? Okay, I have a question related to your fuzzy logic controller. The output of the fuzzy logic controller strictly depends on membership functions, T norms, S norms, and defuzzification method. Have you evaluated different types of T norms or different types of membership functions in order to obtain maybe better results than yours?
And
Because your membership functions looks like triangular one and trapezoidal one. Yeah.
okay, triangular one.
Yeah. But have you checked different types?
No.
Another type of the
No.
membership functions? No, only this one.
Only this one.
And only standard Mondami
Random deducted, yes.
rule. Okay, so we have not checked it. Questions? If not, thank you again. And let me ask Professor Bogdan Miedziński to present detection of the trench depth based on a differential inertial sensor technology. Okay, take your time.
Thank you very much. Thank you, Professor. Ladies and gentlemen, there's one lady, two ladies. Ladies and gentlemen, nice to meet you. That's tremendous things. Okay. The title of my presentation is indicated here. It also deals with the machinery, and the goal is detection of trench depths based on differential inertial sensor technology. Where is no. Okay. Therefore, first few words of introduction, then of the goal of the work, then the trench depth definition detection method, which was used here. Next, the filtering of signals, since we have to filter the signal to get higher accuracy of the detection. Then is the detection signal, testing procedure, and finally we specify conclusions. Okay, that's the problem is that here is you have machine and therefore to keep a constant trench depths. There's a trench depths here. In the past, it was measured manually. It is very important in agriculture production, gardening as well, and another land improvement. Therefore, they testify the quality of field working. Commonly, we use the manual measurements. In the past, however, they have some advantages, take time and energy. There's a pure consistency and repeatability, and cannot acquire trench depths exactly in real time. Therefore, this is thanks to the development of sensor technology. The intelligent detection methods have been developed. At present, the improved detection method also is being used, but the trench depth is based on the direct measurements using contour wheel on indirect method by means of displacement sensors, inclined ultrasonic sensor, and so on. We suggest using differential trench depth detection system based on inertial sensor technology, which is already proposed. What does that mean? Here we have that's a detecting principle is explained here. There's a machine, there's a trench, there's a road or some study, there's a trench depths. When adjusting the trench depths, the trencher rotates around the pivot here fixed on the vehicle. Therefore, this angle, it depends on these things. Therefore, the angle of the trencher here with respect to the vehicle body indicate direct correlation of the trench depths and the changes under the trench depths varying. Of course, just in a moment you will see that the slope is included, unevenness and everything is already included when we compare. What was done? Therefore, we measure the two angles. One is the angle of vehicle, and another is the angle of trencher, and we compare this angle together. That's we locate here inertial sensors, both on the vehicle and both on the trencher. And look, when we have a slope, the principle of is as follows. Here is one sensor located on the vehicle here, and the measured angle. Another is located on the pivot of the machinery as well, here, and the angle is measured. But we are interested in the difference of angle, difference of the trencher and difference of vehicle. That's an angle which indicate us the slope, not the slope, but indicate the depth of the work. In this way, we can omit the slope. The slope doesn't influence accuracy of work. We have used two inertial sensors. First, detect angle of vehicle body as a reference. Here is located here. Second is detect angle of trencher. Here you can see. And as a matter of fact, through the angle difference, this angle, you can see here. Sorry, this light becomes weaker. But we can distinguish in the vehicle body, detection error caused by the slope can be limited or even eliminated. And then having this angle, basing on the parameters, like you see the mechanical parameters, length, something like this. Here you see length, depth, and location, radius, something like this. We can calculate in a very simple way the depth of the trench depth is able to be calculated. When we have an angle, we have this parameters, location, we can calculate this easily. Of course, that's the main problem, that we get some results, and you know that's we use in this system. We use a three-dimensional accelerator, we use a three-dimensional gyroscope meters, and however, as a matter of fact, we only are interested only with one axis. However, under operation, the machine vibration and everything will influence the oscillation of sensor output signal. That's obvious. Therefore, what can we do? We use to filter it. In this way, we just simulated the operation of a Kalman filter, and it's composed of the two parts. First is a prediction, time update, and the second is correction, therefore measurement update. Therefore, we have these parameters as you see here. Therefore, the filtering simulation is a combined step. Then we have a Q, is a covariance of a measurement, and this covariance of this observation, and these two parameters are very important things. There's a gain, optimal gain. Therefore, you see that optimal gain depends on this state function, something like this, covalence for the given time parameters, and the very important things are these parameters, what you see here. That's covariance of the measurements and the covariance of the observation. And this we have taken this into account. However, we could do it individually to change under simulation to change these parameters, but we decided to squeeze the time. We decided to calculate by taking the given QR ratio like these things. And therefore, we use a MATLAB simulation. In this way, the first filter is simulation. We assumed that we have a we assumed that is the same QR ratio, and however vary Q and vary R and keep the same. Then Q, you see that there's no effect. It's absolutely the same. We have a different QR, and the effect is almost the same. Vibration are similar. Even all the parameters measured for different left each other, and therefore here we have data. And this you can see that with decrease of a Q, variance is little bit decreased, but not specially here you see. Therefore, under the same QR ratio, with decrease of parameters Q and R, variation is a little bit smaller, but filtering effect is seems basically the same. And then, as a matter of fact, filtering simulation was performed, but using different QR ratio. Therefore, as the same, you see that the data variance here after filtering under different value, you can see this parameters. Smaller is this ratio, smaller is variance. Therefore, this better. Oops, sorry. Therefore, this better. Sorry. Therefore, another way that you can see here, that is almost constant like that. Therefore, it's very difficult to predict the dynamics of the signal. Therefore, we assume that our signal is sine wave as expected, or with a noise here. Therefore, in conclusions, when variance decreases from like 7 to something to 2 to 2, and there is a trend that variance will approach to a constant. However, delay comes out, and the smaller Q to R is a longer delay is. Therefore, that's this system was assembled and then was checked in practice in the field. In the field, here you have the machinery, here the machine, a monitor and sensor, the data acquisition module. Here is a wireless transmission module. Here we use a wireless communication network, and the upper computer. Everything is like an upper computer, and then first we check the filtering test. The filtering test was performed using the model of a robot, a small robot in the lab, and to verify result in simulation further. It was an adjustable platform, using 2 sensors. First sensor is located here, simulating these machines. Another sensor was here, simulated another machine. And in the test, a remote control vehicle was used as a carrier. And we check it. As a matter is found out, the checking result, filtering test, show that for the same Q to R, before and after filtering, the filtering effect is basically the same. It's basically the same. But when you have a different QR, filtering effect becomes better with decrease of QR, you see here. Therefore, the best is to decrease it successfully. Next, after testing this filtering system in the lab, we decided to establish some equipment, and we performed the field test. You see, that's a field test, wireless transmission module here. Data acquisition module is located on the machine, the tractor. 2 sensors, one is located here, another located here, trenches here, as you see. As a matter of fact, we observed filtering effect, and this was confirmed that the filtering effect becomes better with decrease of Q to R ratio. And as a matter of fact, we obtained 2 results. One is measured results, and then it detected depths. Then this was measured from the sensing system, and another was detected depths. It was measured by hand. And we please compare that the results are almost very similar. Therefore, the accuracy is very high. The proportional error is around 5%. As for the conclusions, therefore the method based on the differential inertial sensor is proposed to detect trench depths, and we use the inertial sensor are utilized to acquire angle difference through one internal sensor on vehicle and the other on trencher arm. In this way, the trench depths can be calculated with a combination of the angle difference and relative dimensions of the trencher structure easily. And the driver of the machine has on the monitor, everything is already can control the depths of the work. That's a very important thing. And however, to decrease the data oscillation caused by machine vibration and so on, therefore this signal has to be filtered. Therefore, the filter and simulation MATLAB performed. We found that the influence of on filtering effect with the change of that under the same value, filtering basically the same. Such variances after filtering are all around 6 to when this is equal 1. With a decrease in this, amplification and variance of curves after filtering is smaller. When Q to R decreases from 2 to 1, variances reduces from 7 to 3, something like this. Therefore, it's advantage of that. Therefore, this detection system was set up finally, And filtering test was conducted to verify conclusions in simulation, and we found out they are almost coincident. And therefore, the field test was conducted, and error state of measured depths and the detect depths is within 5%. Therefore, accuracy is very high. What confirmed the practical usefulness of the development measuring system for the trench depths detection. Okay, thank you very much for your attention.
Thank you. I open the discussion. Do you have questions?
May I ask about not what you are exactly presented, but about the future steps? Are you going to automatically control the trencher position?
Yes.
And how? You mentioned the delay, yeah?
Yeah.
Changing the parameter of the filter.
Yeah, it involved delay time, yeah.
And how these parameters and this delay will be difficult, how influence the control, how do you feel?
Okay, I don't know just now how it will influence it. Therefore, we have to undertake such a works, to do what's going on. First, it depends on the requirements. What's the accuracy? What's our need for the farmers? What's the accuracy? If accuracy is enough like that, we need not to just to remodel it and to improve it. It would be without any sense, since it costs money. It costs money. However, if not enough, then we consider what's going on. What's going on? First, the structure of the trench, the filtering effect, what's going on, and then the manual is everything, the system observation system, and also do you think I mentioned that in this case we limited only observations just only to one axis, perpendicular to the ground. However, we have a 3D accelerometers and 3 gyrometers. Therefore, we can find out what's going on if the structure is moving in a different way. Therefore, in this case, probably if it will be needed, we will do it. However, somebody has to pay for that. Try to make straight line. Thank you very much.
Yeah, I have another question related to filtering methods, because you have used the Kalman filter. But normally, if we are doing or dealing with accelerometer, gyroscope, and something like inertial sensors, the first raw data are pre-processed with, for example, moving average or median filter with a very short window, in order to eliminate some distortion in the signal. So, have you tried to apply such procedure in your case?
I don't really know, since they probably they did, since this work was done in China. Probably they did, and finally it was some reason that they selected just the Kalman filter correctly without this limitation. But this question is good. That's we will try to do that the best.
Okay.
Thank you very much.
Thank you. More questions?
You are not on the sampling frequency of the accelerators.
I have to look at my paper. Sorry, I don't remember that.
They were sampled synchronously in parallel.
Synchronously, in real time. That everything is in real time.
I think it's based on the MEM sensors.
Yes.
And it usually works like 200 hertz or something.
Something like this.
Something like this.
Yes, but necessarily 200 hertz, or maybe a less frequency is enough.
Perhaps you're right.
So 200 frequency should be very high for such
such a purpose.
Yeah, that's the reason I suggest to pre-process the data to filter the first distortion on the pre-filter and then apply Kalman.
Okay, that's right. Thank you.
Thank you again, Professor.
Thank you very much.
And the last presenter is Vedat Tumen from Turkey, and he is going to present recognition of road type and quality for advanced driver assistance systems with deep learning. Go on.
Hello, welcome to the presentation. My name is Vedat Tümen. I am PhD candidate at Fırat University and sometime lecture. I am lecturer Munzur University in Turkey. I study this study I did with my supervisor Burhan Ergen, Associate Professor Burhan Ergen in Fırat University, and Associate Professor Özal Yıldırım. This study titled Recognition of Road Type and Quality for Advanced Driver Assistance System with Deep Learning. Outline introduction problems with method deep learning. Proposed dataset, pre-processing, CNN, experimental, and result. Introduction. The realization and classification of the driving environment has become an important topic in many applications. Autonomous vehicle, human-robot interaction, human-machine system. Highways have a very important place in daily life. Roads are being built for vehicle. Roads are one of the most important reasons for the rapid flow of life. Highway, urban road, divided roads, undivided road, powered road, and unpowered road all contribute to transport and pathways. Generally, the road surface of expressway and divided road are more well kept than other road, and their strip and better market and regular. Modern crude technology have been developed and widespread use smart city, vehicle-to-vehicle and vehicle infrastructure communication and intelligent transport system. Design a driver support system to identify the road type and detection of road defect to experiment. Deep learning use method deep learning. Deep learning architecture analysis main feature such as line, age, color, texture. It combines the result of proposed and created object modeling. The most commonly used structure of deep learning are the deep learning networks, automatic encoding, restricted postman machine. Recently, in the field of the deep learning, there is the convolutional network method, high accuracy performance ratio, separate class of features by retrieving the attributes of the data, process the whole image has been used. Deep learning it is an effective system in terms of the both cost and use in terms of recognition of road type and quality by using only camera image. Comparison with other CNN model. Any CNN actually was developed, which is the deep learning method for both road type and disturbance detection. This model name is RTQ CNN, road type and quality convolutional network. Image from Google Street View were used to detect real-world driving environment. Since this image were obtained with a camera placed on the vehicle, it is quite suitable for this work's input data. Road traffic image camera input image in camera detection vanishing point images, cropping image input vanishing point red point top, then CNN model later recognition of the road type and the recognition of the road quality detection. In this study, vehicle integration advanced driver system for advanced driver assistance system. It is an effective system in terms of both cost and uses the vanishing point method with Gabor filters used for determining the road endpoint. Also, some edge detection algorithms were used for extraction the road bound. The road detection process was performed with various combination of these features. Road image dataset, real driving by were used to classify the road type and road quality using real world image. Google Street View image consisting of RGB channel image were taken in every environment and different weather condition. Database address GitHub converted to RTQ CNN. In total, 614 images for the dataset were used to determine the road type in the first experiment study. For the second experiment study, a new dataset was created by taking 138 all-right type image and 139 road defect image. The 640 images were used for H road type classification application, and 277 images were used for road quality detection. For testing and total 614 image. Road quality 277 image used. Road image dataset with five class and A class distort road. Class 1 Detroit image, Class 2 Express road image, Class 3 Paved Street road image, Class 4 Unpaved Street road image, Class 5 Parked Street road image, and Class 6 Distorted road image. Total image size number 5. Pre-processing, the vanishing point method used the pre-processing work on the image that obtained from Google Street View application. Gabor filtering technique that computers the dominant text orientation edge pixel. RAW image, vanishing point detection, red point and blue lines. Then top red point cropping. Finally, result image from model input final image. CNN model convolutional network were used to distinguish the input image from the RTQ CNN model. Feature extraction methods are complex and time consuming. Another alternative approach to using the feature extraction process step is the use on end-to-end process that performs the classification operation directly using pure image pixel. Recently, multi-layer deep learning constructors have begun to be used automatic recognition of image data. The main advantage of this structure is hierarchical acquisition of feature at various levels of the image. CNN models, CNN-based work and its validation, LeNet, such as LeNet, AlexNet, GoogleNet, VigiNet, ResNet, have great achievement in image processing and classification. CNN layers have 5 layers: convolution layer, activation layer, pooling layer, fully connected layer, and softmax layer. CNN architecture wide convolution ReLU pooling. Convolution layer. Imagine you have an image representation as a 5 matrix value and 3 matrix or işte 3 window oriented image. At each position the 3 visits with matrix multiplies the values or 3 window by the image are currently being. Pooling layers very much convolution where I take a kernel and move the kernel of our image. Max pooling and average pooling are the most common pooling function. Activation layers, the activation process is achieved by following a linear filter with a non-linear activation function applied to each component of the feature map. ReLU, the most common method used in CNN model is ReLU, zero threshold ReLU model activation function used ReLU. Fully connected layers, neuron is fully connected layers, fully connection to all activation in the previous layer as seen in regular neural network. Finally, softmax layer. This is successful classification method for the classification of multi-class data. It is especially used to high number of the class data. Even though the number of classes in a normal classifier is very low, softmax can classify over classes. Mathematics. Experimental result. Two different experimental studies were performed. The first was an automatic classification of the road type in this experimental study. Image data of 5 classes were used. The second experimental study was to determine the road quality. In the second experimental study, a class F dataset containing distorted road image and a mixture of class A, B, C, D, F, E non-distorted image was used. Furthermore, under each experimental study, 2 different datasets were used. The first of these include image without any processing, and the dimension of the image in the dataset were raised. A single CNN model was used at experimental study. This CNN model is a new model designed for this work and called CNN as mentioned previously. CNN or model, the design model 7 convolution, 7 pooling, and 7 ReLU layers. Our model consists of 2 blocks. Repeat 3 times in succession of convolution, pooling, and ReLU layers. The last block, the number of kernels of 128 for the first convolution layer and 32 kernel of 3 dimensions were processed with 2 strides on the image data. Experimental 1 road type classification. Image with the dimension 5 road types. Use of 520 image for training and 128 image for test. Performance 82%. Okay. The reticule model performance VP yani vanishing point 19% other Higher achievement of the proportional dataset raw data and VP model other model recognized problem model high confusion matrix Y average accuracy 91%. Experimental rod quality classification 19% rod quality classification bed rod image dataset. Result rod type 19 and rod petrols rod 99% accuracy. Thank you for your participation.
Thank you. So we are just on time, so maybe one very quick question if you have right now. If not, so I have to close the session. It's 3 p.m., so it's coffee break time. Thank you.
Thank you.